So last Tuesday, we have derived the two-dimensional wave equation in polar coordinate system. Okay, and so we see that the radial distance r is confined in between 0 and r, and including the right end r there, and the horizontal angle theta is the from minus pi over 2, including minus pi over 2 up to 3 pi over 2 there. And the time parameter will be the same. Okay. All right. And with boundary condition, with a boundary condition that u r theta t is equal to 0 for all theta equal to 0 here, right? Which means that the circular membrane is fastened at the boundary of the circular disk. And two initial conditions, right? So this u tilde theta at time 0 is equal to fr theta. Okay, for all r in between, for all 0 to r in between 0 and capital R, and theta in between this interval, and so this is the first initial condition is about the initial displacement, and the second one is about the initial velocity. Okay, at time equal to 0. Okay, so that is the two-dimensional wave equation. Now, when the initial displacement f of r theta and initial velocity g of r theta are radially symmetric, i.e. f r theta is equal to f of r. So the initial displacement depends only on the radial distance r, okay, the r, and independent of the horizontal angle theta. Similarly, for the initial velocity, okay, depends only on the radial distance r. Okay, so in this case, so we will determine, you can see that the solution will be dependent on theta, and will be dependent only on r and independent of theta. Okay, so we will determine solutions of the boundary value problem. Okay. the form U delta R theta T equal to U delta R T only. That are radially symmetric. Alright, so in this case, we will have that the partial derivative of U tilde with respect to theta will be 0. And our boundary value problem becomes here. So we will write down that U tilde equal to C square U tilde plus 1 over R U tilde for integrate over 0. So this is called 12.10.1. Okay. And with a boundary condition, so with a boundary condition that U tilde R T equal to 0 for all T equal to 0. So this is 12.10.2 and 2 initial conditions. U tilde R 0 is equal to f of R for all R in between 0 and R, and U tilde and the first order partial derivative of U tilde with respect to the term variable becomes GR. Okay, so this is 12.10.3, 12.10.4. All right. Now, so you can see that the two parameters T and R, you can see that they actually each of the parameters in an interval. Okay, so that as you can see, which means that R and T were in the Cartesian product, okay, of two intervals. Okay, right. So this suggests us that we can apply the method of separating variable. All right. So we will use the method of separating variables. Okay, so step one. Okay, right. right? So relate U tilde RT to be WR and GT. Okay. RT is E. Okay. And alright, so by 12.10.1, okay, so from here, so we have W G dot dot equal to C square, and the G of double prime plus 1 over R double prime here. Okay, and so now this is becomes to G, and the second derivative of G divided by C square G equal to 1 over W double prime plus over R double prime here. And now so that we said this is equal to minus mu, so this is a constant here. Right, so we obtain two ODEs, okay. Right, and G dot plus mu C square equal to G equal to 0. So this is 12.10.5. The other one is double prime plus 1 over R double prime plus mu W equal to 0. 6 here. And now when we look at this one, we see that we can rewrite it into a Stern-Liebowitz equation. Okay, so this would be R the prime. How can you do that? Well, you can multiply R on both sides, right? So this is equal to R double prime plus double prime plus mu and R W equal to 0. Okay, and then this is actually equal to R the prime plus minus 0 square divided by R plus mu R W equal to 0. Okay, and you can see that this is the Basel equation, okay, of order mu equal to 0. Okay. Okay, so we specifically we write this way, okay, as the in the Stern-Liebowitz as a Stern-Liebowitz equation. So we have dealt with this equation in section 11.5, okay, before. Okay. So as discussed, in section 11.5, a general solution of 12.10.6 of this Bessel equation of order 0, okay, is here, is WR equal to C1, G0, R, with parameter mu, okay, parameter mu, and plus C2, Y sub 0, R with parameter mu. Okay, and well, we know that G0R mu is equal to the summation, okay, equal to 0 to infinity minus mu, case power, and 2 to the 2 case power, k factorial x to the 2k, and the y 0 is equal to 2 over pi G0 R mu log n R2 plus this is R, and then gamma here plus 2 over pi summation k from 0 to infinity minus mu k minus 1 hk, and here is 2 to the 2k, k factorial x 2k here. Okay, and with h0 is equal to 0, and h sub m is equal to summation I from 1 to m 1 over I for all n will equal to 1, and gamma is the limit of m goes to infinity hm minus logarithm of m. Okay, so this is called the Euler constant. Right, so this information has been written in section 11.5. Any questions? Now, when we look at the now we look at y sub 0 in section 11.5, we see that when r goes to 0, okay, so when r goes to 0, okay, the y0 r mu is equal to minus infinity, okay. The reason is here, as you can see, when r goes to 0, the natural logarithm goes to minus infinity. So this term goes to minus infinity. Okay. Even though J0 goes to some number, okay, or final number there, but this goes to minus infinity. Oh, by the way, I forgot, this is R. Okay. This is there. Okay, and for R goes to 0, this goes to 0. So the only thing we have explosion is in here. Okay, so as R goes to 0, then this goes to minus infinity. And so that means that this is not a physical solution. Okay, so we must have that C2 equals 0. Okay, C2 equals, if C2 is not equal to 0, then the solution WR will goes to minus infinity, which is not a solution physically. Okay, and then so that the WR is actually equal to J0 that C1 J0 and the mu here. Okay, so we have this one, and so now we go to step 2. Okay. The boundary condition is here. So keep it as that, and so which implies that, okay, because that g of t is not identical to 0. Okay, so this is not a 0 function. Okay, so which implies that WR must be 0. Okay. Okay, so this is 12.10.7 here. Okay, now when mu is destined equal to 0, okay, the J0 mu will be positive for all R positive. Okay, which violates the boundary condition in 12.10.7. Okay. Because that now the W function is proportional to J0, and so that you can see we have that. Okay, so of course C1 cannot be 0, because if C1 is 0, then this is the trivial solution, right? And so which means that mu, if mu is less than or equal to 0, then So which maybe I will say that now Z equal to WR, which is C2, and J0 mu. Okay. Implies that the C2 is 0. Okay. Which shows that there is a trivial solution. Dump equal to 0. Okay. Okay. So when mu is non-positive, then we have only trivial solution. Okay. So the R is 0. Okay. So now we consider mu equal to k squared with k equal to 0. So now the boundary condition in 12.10.7 required that 0, okay, equal to C1 J0R k squared. Okay, and we require if C1 not equal to 0, then J0R k squared must be 0. Okay, but this implies that J0 KR equal to 0, since we know that we have the identity that J mu x and the k square is equal to 1 over k mu and j mu and the kx. Okay, so we have this identity, right, as shown in section 11.5. Okay, so we have this identity, and we know this is the Bessel function of the first kind of order mu equal to 0. Okay. So we require that J0 of KR should be equal to 0. Right. And so KR should be a 0 of this Bessel function. And we note that the Bessel function of the first kind of order 0 is like here. Okay, so this is J0x. This is x here. And the first 0 is called alpha 1. This is alpha 2. So we call 0, 1. alpha 02, alpha 03, and here is minus alpha 01, minus alpha 02, minus alpha 03. Okay, so 0 means that this is for the basic function of the first kind of order 0. Okay, so we use the two indices to indicate the zeros. Alright, so we let alpha 01, alpha 02, etc. be the positive zeros of J0 of X. Okay, so we know we have infinitely many zeros for basic function of the first kind of first order. So we have that. Okay, and so that then K R should be equal to alpha M equal to 1, so that we have Km defined by alpha M divided by R for M. Okay, so when the parameter, when the K is equal to K sub M, okay, then we will satisfy the boundary condition. Alright, and so we obtain W sub M R defined to be J0 and K sub M R. Okay, so this is J0 alpha sub M big R and little r here. Okay. Alright, so we obtain which satisfies the Bessel equation in 12.10.6 and the boundary condition in 12.10.7. Okay, so we find countably infinitely many solutions for the Bessel equation as well as the boundary condition. Okay. Now we want to solve for the second ODE here in 12.10.5. So now, so with mu sub m equal to we know that is k sub m square, which is equal to alpha sub m r square, right? So with this parameter, a general, so with mu equal to mu m, a general solution of 12.10.5 is here, is g sub mt equal to a sub m cosine sec sub km t plus b sub m sine c sub kmt. And we will use cosine lambda sub mt. So we use the angular frequency, okay, with lambda sub m defined to be c times k sub n, and which is equal to c times f sub n divided by r. Yeah. Okay, so this is the general solution. Okay, of the ODE governing the time evolution here. So G is a function of t here. Okay. Any questions, September? Okay, and so hence, okay, we have m r t defined to be sub m r and the g sub m t. So this is actually a sub m cosine lambda mt plus b sub m sin lambda mt here, and g0 and the k m r here. Right? So that are eigenfunctions are called the eigenfunctions of the boundary problem corresponding to the eigenvalue lambda sub m, which is c sub km, which is c alpha m divided by r for all m greater than 1. And another name for u tilde t here, u sub m, this is called the m's mode. So the m's normal mode of the vibration of the circular membrane. Okay. And we know, so these functions, so which satisfy the two-dimensional wave equation in 12.10.1. Okay. And the boundary condition in 12.10.2. Okay. So now we go to step 3. Right, so since the wave equation in 12.10.1 and the boundary condition in 12.10.2 are linear and homogeneous. The superposition so a superposition of U tilde n T so we call URT define to be which is equal to also satisfies 12.10.1 and 12.10.2. Okay, provided that the series converges. Okay, and the series of termwise partial derivatives okay converges to the corresponding partial derivatives of the sum U tilde RT. Okay, so that 12.10.1 is satisfied. Okay. And the A sub n, B sub n will be determined by the two initial conditions. Okay. Now setting t equal to 0, we have okay, by, or I say, by the initial condition in 12.10.3, we have that U tilde 0 is equal to, and for t equals 0, so So this is 0. And cosine 0 is 1. So we have a sub m. And the j0 r sub m r. And this is equal to f r. Okay. So which is the Fourier Basel series expansion of f of r. Okay, with respect to the orthogonal system. Okay, as we discussed in section 11.6. Okay, we have shown that actually we can have the expansion. So this is called the Fourier Basel series expansion. Okay, and we know how to find the coefficient, right? So that an would be 2 divided by r square, and the j1 square of alpha sub m here, and this is r 0 r f r, and the j0 alpha m r and dr. Okay, for all m greater than equal to 1. Okay, so we know how to find that. And also with the initial condition in 12.10.4, so we have that u tilde t r0 is equal to summation m from 1 to infinity lambda sub m and bm j0 alpha m okay, equal to gr. Okay, and this is because that if we take the positive derivative, so this is becomes 2 minus lambda m am sine lambda mt plus lambda m bm cosine lambda mt, and the j0 also m here. Okay, because we assume that the termwise positive derivatives, the series of termwise positive derivatives converges to the corresponding positive derivative of the sum. Okay, so we have this one, and when we let t equal 0, then this is 0 here, and cosine 0 is 1, so we have lambda m bm times j0. Okay, so we have this one, and once again, which is the Fourier Basel series expansion of the initial velocity gr. again with respect to the orthogonal system J0 alpha m and where we can find B m. So that lambda m Bn is equal to 2 divided by r square and J1 square alpha m integration from 0 to r gr and J0 alpha sub m divided by r, big R and little r here, and dr. Okay. Okay, so we are able to find M and B. So we have now actually a unique solution now. Okay, so because this is a physical problem, so with the initial condition and then the two with the boundary condition and the two initial conditions, then we should have a unique solution. Okay, and so by the method of separating variables, now we have the solution. You know, and of course that you have to justify, as I say that you have to justify that the series actually converge, right? And also the series of pairwise positive derivatives will also converge to the corresponding positive derivatives of the sum. Okay, and this is quite similar to what we have done before. For example, in section 12.6. So you can apply the theorems we have in section 11.3 to justify that the provision here is actually true. Okay. Okay. So that is the solutions we have. Okay, and so we will take a short break to 2:25. Okay, so in the next section, we will consider three-dimensional Laplace equation in cylinder and spherical coordinate systems. So alright, so now the three-dimensional Laplace equation in Cartesian coordinate system is here. Uxx plus uyy plus uzz equal to 0. So this is in Laplace in Cartesian coordinate system, the standard coordinate system xyz. Okay. Now, and in many situations, we because of the boundary problem that's for example, it's quite often occurs in EM theory that we will consider some conducting material and as a cylinder, or conducting material as a sphere. Okay, so that they are regions that is not rectangular regions. Okay, and so it would be more appropriate to consider the Laplace equation in cylindrical coordinate system or in spherical coordinate system. Okay, and in many situations we can still apply the method of separating variables to solve the problem. Okay. So the first one, I'd like to see that if we transform the Laplace equation from the Cartesian coordinate system to cylindrical coordinate system. Right. So the first case is here. And for that, so that the coordinate system, so x, y, z, will goes to the r theta and the z here. Alright? And here, that the x is become to r cosine theta, and the y becomes to r sine theta. Okay, and z will be the same. Okay. Will be same there. So the xy is, as you can see, xy, if you focus on the xy plane, that what you would have done is just the polar coordinate transformation only, as we discussed in the previous section. Okay, so you can see that in this case, the Laplacian, so that we will let it tilde theta and z defined to be u x theta z, y theta z, and z theta z. Okay? So here. So then u x y z becomes to u tilde x y z and the theta x, y, z, and the z, x, y, z. Okay, with that. Okay, so that so now the Laplacian, right, the u, right, the Laplacian u, it comes to u tilde, and so this is the second order partial derivative of u tilde with respect to r plus 1 of r and tilde. So this is the first order partial derivative plus 1 over r square, and again this is the second order but with respect to the theta here, and finally z square. Okay, alright, and this is 0 here. Okay, so the Laplace equations in the cylindrical coordinate system becomes to these equations. Okay, and in this section, we will coordinate system. The transformation is quite similar to the polar coordinate transformation in 2 dimensions. Okay. Now, spherical coordinate system. Okay. So in here, the Cartesian coordinate will transform to the radial distance, and the horizontal angle, or sometimes called azimuthal angle, and also the elevation angle theta, or vertical angle, or polar angles. Okay, so this is the polar angle, and this is azimuthal or azimuth angle. Okay, and this is the radial distance. Okay, so that as we know, for a point here, so now the projection. Okay, so this is a point x, y, z. This is x, y, and z. Okay, and this is the azimuth angle, or the horizontal angle we have, and this is the polar angle. Okay, so the polar angle is counted from the z-axis to there. Okay, so that is the angle we have, and this is r. Okay, the radial distance from the origin to the point P here. Okay, okay, and so the coordinate transformation is r. Oh, I see. So okay. I'm sorry. In here, I use theta as in as in our previous notation. So this is theta is azimuth angle, and the polar angle will be called the phi here. Okay. All right. So that this is cosine theta sine phi. Y is r sine theta and sine phi, and z is cosine phi. Okay. Alright, so this is the coordinate transformation. And once again, we define a new function, U tilde r theta and phi is equal to x theta phi, y theta phi, z theta phi. Okay, and u x y z, it's u. So define this one. Okay, and u tilde x y z and theta x y z and phi x y z. Okay, here. Okay, and then you will use the find the proper partial derivatives as we have done in section 12.10 in the previous section. Okay, so that the parsing of u. Okay, so the parsing of u. The parsing of u. When we do the coordinate transformation, then we will have here u tilde plus 2 divided by r u tilde plus 1 over r square. So here you can see 2 divided by r instead of just 1 divided by r. Okay, and this is so this is the phi square. Okay, u tilde plus cotangent phi r square phi u tilde plus 1 over r square sine 5 and r square u tilde. Okay, and we can simplify this. This is r square and r square u tilde plus 1 divided by sine phi. Okay, and 5 sine 5 u tilde plus 1 over sine square 5 and sine square u tilde. So some computation should be taken, and so that we will get this formula. Alright, and so now we consider we'll consider Dirichlet boundary value problem in a spherical coordinate. Okay, so we will consider such a problem. Alright, so we assume that we have circular symmetry, namely that U of R theta phi is equal to U tilde R phi. Okay, so that the solution is independent of the horizontal angle theta, all right, or the azimuth angle. Okay. All right. In this case, right, so all the boundary conditions should have a circular symmetry. Okay. Right, so in this case, the partial derivative, this signal of the partial derivative must be 0. Okay, so that this term disappear. Okay, and then that the Laplacian becomes to be R square of plus 1 over sine 5 and sine 5 okay, right, this is equal to 0 because this term disappeared. This term disappeared. Okay, so this is called 12.11.1. Okay, and with an explicit boundary condition at R equal to big R here, that U R phi is equal to f of phi. Now U of phi is the polar angle, okay, from the z-axis. Okay, for all 0, phi, and pi. Okay, so this is 12.11.2. Okay, and either, okay, implicit boundary condition at R equals 0 for interior problem. Okay, so that this problem will be U tilde 0 phi is finite. Or 0 pi 12.11.3 over so maybe I will write right here, and an implicit boundary condition either at I equals 0 or at I equal to infinity for x. So we will see maybe go to 0, okay? So the limit is finite, okay? And for the exterior problem, we have a limit goes to infinity e to phi, okay? Will be 0 for all 11.4. Okay. Okay. The interior or exterior problem is here. Is that so we have a ball with radius r, right? Maybe we will consider a U function which is inside the sphere or inside the ball or outside the ball. Okay. The interior problem is that we try to find a solution inside the ball. And for the exterior problem, we will find solution outside of the ball. Okay, and so we call implicit means that if we consider a solution inside the ball, then as r goes to 0, okay, so the solution must have a limit which should be finite. Okay. Or if, let me see, maybe I will write here, maybe no, that U to R phi is finite, right? Now equals 0. Right, maybe I will say here. Okay. Okay, but this is more appropriate, okay? Sorry. So that the solution should be finite near 0. So that the solution cannot explode, right? So it should be finite. But when r goes to infinity, for the exterior problem, if r goes to infinity, then the solution should go to 0. Okay. So we call either condition as the implicit solution. Okay, by the physical consideration. Okay, by physical consideration. Because that, for example, the U theorem might represent the potential or some field, the force field. Okay, and so at the infinity, the potential or the force field become to be 0. Okay, so this is it's a reasonable assumption there. Okay, and so by the method of separating variable, okay, then we let U tilde R theta to be GR and H of phi here. Okay, and then so that by 12.11.1, so by the equation there, so we have so we have that that H, okay, and R square U tilde plus G and sine 5 okay, so this is sine 5. Okay, this is 0. Alright, so we divide the product. So now we find that 1 over G. Oh, by the way, I forgot. So this is G. And sorry, this is H. Okay. Okay, and so we divide here over G dr, so that the partial derivative becomes to derivative here. So and 5. Okay, and so this is R square d dr G, which is equal to minus 1 over H sine 5 and d5 sine 5 and d5H, which is equal to lambda. Okay, so this is a constant. So this is a constant. Right, and so from there, so then so that we obtain two ODEs. Okay, and the first one would be 1 over sine phi d5 sine 5 dh d5 plus lambda h equal to 0. So this is 12.11.5. The other one would be R square and d square g dr square plus 2r and d dg dr minus lambda g equal to 0, 6. Okay. Okay, so we have this one. Now our purpose is to find a physical solution, so that we want to find a unique solution that it will satisfy the Laplace equation as well as the satisfying this explicit boundary condition when little r is equal to the big R, as well as one implicit boundary condition, either this one at r equal to 0, okay, for interior problem, or at r equal to infinity for exterior problem. Okay, so we just want to find a solution. And when we look at both ODEs, especially the second one, and we'll see that when the lambda is equal to now, so when lambda equal to n times n plus 1, okay, the ODE in 12.11.6 becomes 2 the Euler-Cauchy equation to the Euler-Cauchy equation. Okay, so we write it down that this is r square d square dr square g plus 2r ddr minus n plus 1 gr equal to 0. Okay, so this is so if you study the ordinary differential equation, that you will see this is a famous Euler-Cauchy equation. Okay, and this equation has been well studied. Right, and as we see that for a solution of the Euler-Cauchy equation, okay, we set g of r to be the s power of r, right, and then to obtain the characteristic equation, okay, so we attempt to find a solution which is the power of r, and so that we have an unknown a there. And so now the characteristic equation becomes 2a minus 1 plus 2a minus n plus 1 equal to 0. And so this implies that A is equal to n over minus n plus 1. Okay, so there are two possibilities. Okay, so there are two possibilities there. Okay, and so that we have two possible solutions, right? It's so Gn we could define Gn to be the nth power of R, and we define Gn star R, right, to be 1 over n plus 1. Okay. And as we will see that this is good for with the interior problem, and this one will be good for the exterior problem, as you will see. Okay, because when R goes around 0, then when R around 0, this function is finite, but this function is infinite if R tend to 0. And if R goes to infinity, then this will is bold, but this will go to 0. Okay, so you will see this is good for the interior problem, and this is good for the exterior problem, as you will see there. Okay, so now we have find solutions for the Euler-Cauchy equation. Okay, when lambda xn times n plus 1 here. Now we will solve the other ODE. Okay, so the ODE in 12.11.5 with lambda equal to n times n plus 1. Now to solve 12.11.5, to solve the ODE and 12.11.5, okay, we let cosine phi to be, or just let a new parameter w to be cosine phi here, and then we know that the square of sine phi is equal to 1 minus w square, and also, right, and also if we do the derivative with respect to phi, this is the same as we do the derivative at dw and the dw and d phi. Okay, so we have this. The differential operator has this relationship there. Okay. Okay, and the dw, d phi, give us minus sine phi d and the dw. Alright, so minus sine phi d and dw there. Okay. Okay, and so that 1 over sine phi d and d phi, okay, is equal to minus d dw. Okay. now the ODE in 12.11.5 becomes now here the D and the DW. Okay, and we will look at here. Look at here. This one, this operator, as we see, this operator is equal to dW. Okay, and this operator. Okay, so now D5. Okay, so and right. Okay, so right. So by the change of variable, let me write here. That we define to be h of phi. Okay, so that h of phi, it's h delta and W5. Okay. Alright, and so D5, H5. Okay, becomes to D and dW times dW and D5. Okay, and so the dW, D5, this is minus sign. So this is minus sine 5, and dW dW H delta. Okay, so the replacement, so DH, this one can be replaced by minus sine. Okay, this is minus. Yeah, I'm sorry, I forgot to put minus. And this is sine phi and the DH delta and the DW here. Alright, so minus sine becomes the plus, right? And here we have sine phi square, the square of sine phi. But square of sine 5 is equal to, so it's equal to 1 minus W square. Okay, as we know, right? 1 minus W square. And this is DH delta and the dW. Okay. And plus that term on n plus 1. And the H delta equal to 0. Okay, so now we have this one. Remember, this is our lambda here. Okay, because we consider lambda equal to n times n plus 1. Okay, so with this change of variables, we can turn the ODE in 12.11.5 into this ODE. Any questions? Okay, so the differential operator here, this is equal to this one, right? And the derivative of h with respect to phi is equal to this one. Okay. So this is equal to this one. Okay. Okay. So we have the square of sine phi, but the square of sine phi is 1 minus w. Okay. So this is 1 minus w here. Okay. And what is this? Okay. So this is the famous Legendre equation, Legendre equation. So that so which is the Legendre equation? Okay, famous equations in ODE. Okay, and as we discussed in section 11.5, okay, that a solution, a non-trivial solution for n equal to 0, 1, 2, etc. It's here. It's h tilde w equal to Pn, okay, and w. So Tn is the Legendre polynomial of degree n, okay. So that for all n equal to 0, 1, 2, etc. Okay, so this is the Legendre polynomial of degree n. Yeah. Alright, so we have for each n, we find solutions, okay. Okay. Now we have un phi, which is an as power and the Pn. Okay. Now it's Pn cosine phi. Okay. Because W is equal to cosine phi, right? So we just write it down here. And also U1 star 5, which is Bn divided by by r to the n plus 1's power, and the Pn cosine phi. Right, so which satisfy the Laplace equation in 12.11.1. Okay, so which satisfy this equation. Okay, either this one or this one. Okay, they satisfy the Laplace equation there. Now for the interior problem, so we found, for example, potential within the sphere, okay, with radius r. Okay, now U phi, so we do the superposition. And okay, so this is the and with the boundary condition at r equal to r there, so that is U r phi is equal to An Rn Pn cosine phi equal to f of phi. Okay, well, phi in between 0 and pi. Okay, and we know that which okay, so which is the Fourier Legendre series expansion okay of f phi. Okay, so that we know that N is equal to 2n plus 1 divided by 2 minus 1 to 1. So that's Fw and Pn dw. Okay, or F theta W is defined to be F of phi W here. Okay. Okay, so and okay, all right. So I think. constant. And by the change of variable, alright, so since dw is equal to minus sine phi d phi, so that an becomes to 2n plus 1 divided by 2, and r as power 0 to pi, and f5 pn cosine 5 and sine 5 and d5. Okay. So this is for the interior problem. And for the exterior problem, potential outside the sphere. Okay, so that it's from 0 to infinity, and Pn n plus 1 Pn and cosine phi. Okay, and so with Bn is equal to 2n plus 1 and 2, but r n plus 1 0 to pi f phi Pn cosine phi sine phi and d phi. Okay. Right, and maybe with boundary condition that u tilde r and 5 equal to there. Okay. So this again, this is the full Legendre series expansion again, right? So that we can use what we have learned in section 11.5 to find the coefficient Bn. Right. Okay. Okay, and so our midterm number 2 next Thursday will cover the whole chapter 12 as well as sections 8 and 9 in chapter 11. Okay, and so please read section 12.12. So the section 12.12 is to apply the Laplace transform to solve partial differential equations. Okay, and so I will send you a handout on these sections. Okay, but as a reference. Okay, so you have to self-study on this section. Okay. All right, so I'll stop here.